This computer, okay, I think it's recording. So, all right, so pick back up with the definition of a function. What has to happen, and it's a correspondence, so with that correspondence, each element of one of the sets, which we call the domain, has to correspond with exactly one element of a second set, which is called the range. All right. And frequently in this course, you're going to hear us talk about inputs and outputs. That is not what I wanted to do right there. So, as I said, the first numbers are elements of the domain, and we a lot of times call those the inputs. The second elements from the range are called the inputs. All right. So here you see an example. The relationship between Celsius and Fahrenheit degrees. We see this in the table. For example, right in the middle of the table, 0, that's the freezing point in Celsius degrees. 32 Fahrenheit is freezing point. At the far right of the table, that's the boiling point, 100 degrees Celsius, 212 degrees Fahrenheit. So there's a relationship between the degrees, and we can actually figure out what that will be in a minute, or later actually. So it says write the relationship in the table as a set of ordered pairs. So let me just, now can you guys see me writing ordered pair? Please say yes, someone.
Yes, ma'am.
Okay, great, thank you. Because if that didn't work, we'd have to stop and start all over. Okay, so an ordered pair is just that. It's a pair of numbers, meaning the order of them is important. The first number in the ordered pair, and you know, in an algebra setting, we talk about X and Y. We don't always use X and Y, and that's why we want to stick to the word input and the word output, okay? Because it's not always X and Y. But that's what an ordered pair is. That's what we mean. Okay, for a set of something is indicated with these, those are actually called braces. I think some people also call them curly brackets. Official name is braces. Now that indicates a set. And then I would just write, okay, for the negative 20 degrees Celsius, we're going to assign negative 4 for the output. And then with negative 10, we assign 14, and so on. So in each case, we're just taking that Celsius temperature and pairing it up with its corresponding Fahrenheit temperature. Okay. It's a pretty simple concept, but it's an important concept. Because like I said, everything we talk about is going to be a function. All right. So that's our set of ordered pairs. Then it says write the domain. That's going to be the set of all the inputs. So again, for set, I'll use that curly bracket. And I'm just going to pick up all of the inputs from the table. All right. So basically, whoa, stop doing that. The inputs are up here, and the outputs are there. Okay. Okay, the range is going to be the set of all the outputs. So again, my curly brackets and just simply listing all the second elements from the ordered pairs, which are also all the numbers in the bottom row of the table. All right. Okay, so let me let's see. Okay, next question. Does the table define f as a function of c? So let me just say, here is the informal definition of the function. In other words, this is kind of an easy way to look at, especially if you just have a set of ordered pairs. The rule is that no inputs can repeat. All right, so that's a pretty handy thing to remember. So looking up there at the inputs, are any of those repeated? At this time, I would probably.
No.
Okay, correct. Thank you. So since no inputs repeat, I can say, yep, this is a function. And actually, the function, let me write this out before I mess up my words. F is a function of C, okay? A function always expresses a relationship between two variables, all right? So you can't just, it wouldn't be correct to just look at that table and say that's a function, because that's not enough information. It's always got to be X is a function of Y or Q is a function of S. There are always two variables involved, all right? And that's why that informal definition is useful, remembering that you're talking about the inputs. Okay?
Is Yoko?
Yes?
So when it says does the table define F as a function of C, does F and C stand for Celsius and Fahrenheit?
Yes.
Or are those just random letters? Okay.
Yes, and you have a good point. Definitely the variables should be defined. So yeah, that's a good point. Ooh. All right. Okay, so the next part says, okay, I mean, this is a well-established fact in the science world. There is an equation, which is also a function, that shows this relationship between the Celsius and Fahrenheit temperature. That F equals 9/5 C plus 32, okay? So that's the function that gives the rule, that's a rule. Or equation, all right? Okay, next, you see two figures side by side. This first one is what we call a scatter plot. And a scatter plot is nothing more than a set of ordered pairs. Was that defined? Wasn't. Okay. So the graph of the ordered pair is called a scatter plot. And then beside it is the scatter plot along with the graph of the function. The scatter plot, well, I do know how to spell scatter plot with the function. Okay. All right. So let me also mention, hopefully this is recording, but also I will save this document and post it up on D2L. There'll be a separate folder that says notes from class. So you can go in, I'll just post this up there and you can see, this document when I'm finished with it. All right. Oh, all right. Part F is kind of jumping the gun a little bit. Let's wait on this, okay? Because we're going to talk about, you can see at the bottom of the screen, we're going to talk more specifically about domains and ranges in a minute, all right? Okay, and then the last part, suppose a child's normal temperature is 98.6 degrees Fahrenheit, and the only thermometer available, which is Celsius, indicates that the child's temperature is 37 degrees Celsius. Does this reading indicate that the child's temperature is normal? All right, so basically, what we're trying to do here is find the Fahrenheit temperature that corresponds with the 37 degrees temperature. That corresponds with 37 degrees Celsius. All right, and to do that, we just do a little simple substitution. In the equation, we substitute 37 in the equation. And just gonna bring out my calculator real quick and put 9/5 times 37 plus 32. Sure enough, it comes out to 98.6. And so yes, does this reading indicate that the child's temperature is normal? That is a normal temperature. All right. Again, stop me if you have a question. I'll keep going. Okay, so specifically, well, I already mentioned, but here's another way we refer to X, remember, as the inputs. More formally, that's called the independent variable, and Y, which would be the outputs, or the output, that's called the dependent variable. All right, and so when if we define, hang on a second. Boy, it makes noises too. All right, so if we say, suppose we say Y is a function of X, then X is going to be the independent variable and Y is the dependent variable. Okay. We can also, in less formal terms, we can say Y depends on X. All right. Y is dependent on X. All right. Okay, that bumped to the next page. All right. So next, the The next thing we see right here says if the domain of a function is not specified or restricted by the context in which the function is used, it is assumed that the domain consists of all real numbers that result in real number outputs in the range. So that's, again, that's kind of some formal language there. So maybe let's just look at some examples that might clear that up. So for these examples, we're looking for the domain and the range. All right. So what we have in this first graph, remember that's called a scatter plot. Probably should have made this a little easier to read. Let's go in and label the coordinates of this point, these points. So this first one on the left, so to get to that point, I go -6 on the x-axis and -7 on the y-axis. So those would be the coordinates of that point. All right, the next one, that's going to be -3 along the x, -2 along the y. So that's -3, -2. Way up here at the top, starting at the origin, I go -1 on the x and 6 up. So that's -1, 6. This point is actually on the y-axis. That's the point 0, -2. Now 3 along the x, 5 along the y, so 3, 5. I think I'm getting them all. And then this last one, 5 units along the x-axis and -7 on the y. I think that's what. Oh, look at me. They're right over there in the table. Well, okay, I wasn't paying attention, but okay. So, but that's fine. That matches up with the table, so that was kind of overkill. Okay, so the domain will be all these numbers in the x column. The range will be all the numbers in the y column. All right, and so let me just specify something that here we're in a typical graphing system. Let's see, I'm not real good at drawing lines. So let's see. Insert shape line. I won't let me do that. And also, let me say, for the way that the textbook is set up, so we're working in chapter 1, in the first section. At the beginning of each chapter is something called the algebra toolbox. And a lot of these things I'm talking about, specifically right now, the way that things are set up in graphing, those topics are in that algebra toolbox, all right? And those of you that are in the support class, that's what you all will be doing in addition to the assignments for this class, if that makes any sense. Okay, so, whoops. Okay, now it's going to start misbehaving. Whee. All right, so I have to be careful where I put my hand. This is not good. My drawing icons just went away. Okay, there they are. All right. I talk to myself a lot here. That's okay, I guess. All right, so these are called the axes, the horizontal axis and the vertical axis. The point where the two axes meet is called the origin. So you may have heard me say that a minute ago. All right. So from a graphing standpoint, that we talk about the ordered pairs X, Y, all right? Doesn't have to be X and Y, but that's just standard how we label the variables and the axes, okay? Any question before I go to the next graph?
No.
What's that?
Help us, Lord.
What? I'm sorry, what?
You could go to the next graph.
All right, thanks. All right, so for the next graph, now what's different? The graph we just looked at was a just a specific set of ordered pairs. That's what the dots indicate. Those are points on the graph. In part B, this is what we call a continuous graph. All right, it's continuous. And in actuality, this contains an infinite number of points. Seems a little strange to think about that, but that's true, okay? It's kind of an abstract idea, but it has an infinite number of points. It does have a specific starting point and stopping point.
And that's B, right? B is the continuous graph.
That's right. B is a continuous graph. And so a lot of times, you know, I'll say, okay, this one has a starting point and it's indicated by that closed circle. That means that that's specifically where it starts. And it also has a specific stopping point. All right. The way that affects the domain and range is, let me get a little more room in here. The way that affects the domain and range is that the X's and Y's also have a definitive starting point and stopping point. So I might say the X's start at -3, which is right here, and stop at +3 right here. Okay. So if we were just talking informally, we could say, hey, the X's go from -3 to +3. The way that we write this is to write it as what's called an interval. Which looks like that. All right, and that is basically, maybe more room. That's basically how we write. That's the set of numbers from -3 to 3, starting at -3, stopping at 3. Okay, that's how we write that. Now, if we talk about the Y's, okay, well, it's not very good. I should have probably made that a little better. Let's say, I'm just say that's negative 28. Because I don't really know what I'm going to just say, hey, that's negative 28. So the y's start at negative 28, and here's the stopping point. So they stop at 40. All right. So we'll say the y's start at negative 28 and stop at 40. And I'm going to write that as an interval. Negative 28 to 40. Okay. And let me just make this other sort of observation. I think I'll write this over here. The interval, whoa, this thing does some crazy stuff. Popped my E right up there. It's very sensitive. Try it again. All right, the interval indicates a continuous set. All right. So again, when I write that interval, the negative 3, comma 3, that means all the numbers between negative 3 and positive 3. All right. Let me know if you have a question on that one. Part C, which is the other figure, the difference here is the arrow on the end of the graph. All right. What does that arrow mean? You probably know. The arrow,
That the points keep going on forever.
you got it exactly. The arrow indicates that the graph goes forever in that direction. So if I said, okay, does this graph have a starting point? It does not. It keeps going forever and ever to the left. So we need a way to write that. All right, so let's say the x's have no starting point. So we say, and this is a little, I'm just gonna write it, it's kind of funny looking. We say it starts at negative infinity because that's our symbol that means all the way to the left. All right. Here's the stopping point on my graph. And that is the ordered pair 4, 0. So where do the x's stop? At 4. All right. So when I write the domain, this is how I write it. The set of numbers from negative infinity to 4. All right. Now, why did I use a parenthesis on one side and a bracket on the other? I forgot to mention the brackets. Well, a bracket, a little information box here. And an interval a bracket left or right means that number is included a left or right parenthesis means the number is not included.
Wait, I have a question.
Okay,
So if it was facing the other way, the starting point would be positive infinity, right?
that would actually be the stopping point.
Oh,
You mean if it looks something like that? Is that what you mean?
uh, hmm, I have no clue. I'm lost.
That's okay. Um, yeah, I mean, it's either going to extend all the way to the left or all the way to the right. And sometimes it goes both. Sometimes it extends all the way in both directions. A lot of times it does. So what I wrote over there in purple, we're saying, okay, in this set of numbers, 4 is included. And that's because there's the closed circle on the graph says, hey, we go all the way up to 4 and we include the 4. Because negative infinity is not a number, we can't include it because negative infinity is just a symbol to indicate, hey, this thing keeps going forever to the left. All right.
That's
All
if
right.
it was. That's what I meant. If it was
Okay.
going to the right, would it be positive infinity
If it was going what?
to the right?
Yes, you're correct. It would be positive infinity. Yep. Okay. And then the range. All right. So for the range, those are the y values. The y's actually start at 0. Good grief. Drives me crazy. I'm sorry. Like I said, it's really sensitive. If I touch, what is going on now? If I touch anything on the side of the computer, it just goes crazy. The y's start at 0 and go to up forever, if that makes sense. Go up forever. So for the range, we're going to say starting at 0, going forever up. Okay. A little confusing maybe. Let me give you one other little sort of tip. When looking at the graph, when you're speaking of the domain, you're looking at the graph from left to right. And then when you're looking at the range, you're looking at the graph from bottom to top. All right. Okay, any question before I move on?
Ma'am,
Yes? No, ma'am?
I'm still a little confused about the brackets and the parentheses.
All right.
Like,
Okay.
not understanding it a little bit.
Okay. So let me take a minute. We'll talk about that. So the brackets and so forth, those all have to do with what's known as interval notation. So these are just some examples, just making some things up. So suppose I wrote this, -3, 5. That would mean numbers from -3 to 5, including -3 and 5. I'm assuming this is what you're asking, but tell me if not. All right, if I put -3, 5, and a parenthesis there, I'm still talking about the numbers from -3 to 5. I'm including the -3, but not the 5. Does that make sense?
Yes, ma'am.
Is that what you're asking?
I think so. Yes, ma'am.
Okay, and then from a graphing standpoint, just suppose I had this little graph right here, and suppose that's 4, and this is -2, and -3, and this is +2. This is 3 right there. All right, so from a graphing standpoint, what does the open circle mean?
It stops.
Okay. And the point is not included.
Oh,
Okay. And then a closed circle means that the point is included. Okay.
yes, ma'am.
So suppose I wanted the domain of this little graph. Now, this is separate. This is just a separate example from what I did up there. All right. So where do the x's start? At -2. Is the -2 included?
Yeah.
No.
Oh, no.
No, it isn't, because it's an open circle there, which means the point is not included. So that means -2 is not in the domain. Stop that. I don't know what I just did here. I want that to go away. Okay. So my domain starting at -2, stopping at 4. The -2 is not included, but the 4 is included. You know, and honestly, guys, this is really overkill for us for this course. I mean, we're not typically going to be looking at stuff that's like this. All right, so for the range, the y's start at -3, but there's an open circle there. So we put a parenthesis to indicate that. So the y's go from -3 to 2, -3 not included, 2 is included. Okay, does that help?
Yes, ma'am.
Okay, good deal. And like I said, that it's kind of overkill, but that's all right. Okay, So now we're going to look, okay, in the next example, this is a table of data. Actually, this is actual data from the U.S. Census Bureau that shows the number of female physicians F. So that's being indicated by the variable F. Let me put an F over here. And shows the number of female physicians in thousands in the year X. So the year is X. And this is X and this is F. So this is just, in the textbook, we double up the tables like this to save room. It's kind of confusing. I meant to change that. So this column here is just a continuation of the year. And this is a continuation of the number of physicians, okay? So just all we're asking here is F a function of X? If so, which of that, now this is what's important, which of is X or Y the input? Back up for a minute. So if F is a function of X, X is the input and F is the output. And then what was the informal way to decide if something is a function? Do any of the inputs repeat? Inputs being X, which is the year. Do any of the years repeat? No, we got 2015, 2018, so on and so on. So if the answer is no, what does that tell us? The fact that no inputs repeat, then F is a function of X. Okay. All right, for the next one, okay, so there's a scatter plot, and to the left of the scatter plot is the set of ordered pairs that goes along with that. All right, so we're asking the question, is P a function of X? So P is a function of X. Which of those is the input? P is going to be the output. X is going to be the input. Now, it's not because it's an X. It's because if P is a function of X, that means P depends on X. So P is dependent on X. X is the input. All right, here are the inputs. Do any of those repeat?
No.
So what's confusing about this one, or what might have led you to answer this incorrectly? Well, let me go ahead and answer it. So do any X's repeat? No. Therefore, come on. If no X's repeat, then P is a function of X. Try not to touch the sidebar. So what would throw you off? If you just looked at this, you would say, over there in the P column, some P's repeat, don't they? We got 1800 showing up twice and a 1050. So do we care? No. the outputs can repeat as much as possible. Doesn't matter. So it doesn't matter that the outputs repeat for something. Does not matter if, come on, I need a new platform here. Does not matter if outputs repeat. Don't care. All right. All right. Okay, looking at C. Now this time we're saying the number of tons X of coal sold is determined by the profit, P. So here's my question, is X a function of P? So again, the letters might throw you off, but the letters don't matter. If X is a function of P, then P is the input and X is the output. All right, this time, do any of the inputs repeat?
Yes.
Yes, they do. And all it takes is one example. So the negative 100,000 is an input and repeats. So the answer is no. X is not a function of P. All right. You with me on that one? I'm going to skip D because that's kind of open. That needs to be written a little bit better, and I forgot to do it. So we'll just skip that one. All right. All right, any questions before I go to the next one? What is the next one? Okay. Going to example 4. These are problems that, and you're going to see this sometimes. You're going to be questions, and I'm going to say, all right, this is going over into the algebra world. We're not really interested in that, so I'm just going to tell you the quick and easy way to tell whether, just give them an equation. Now, if they don't use X and Y, we can't really answer that. So I'm going to say, for an equation with X and Y, like this one. Notice the other things weren't equations. There were graphs or tables, but when you just look at a point blank equation like this, if you have a y squared, it's not a function. Or I should say y is not a function of x. Let me back that up. If you have a y squared, then y is not a function of x. All right. So like I said, this is not, this is here, but it's not really what we're particularly interested in. So what's the answer? No. All right. Got a y squared in it. How about part B? Is there a y squared?
No.
There is not. So is that a function? Yes. Okay. All right, now we're going to just take a look at graphs. How do we tell if a graph is a function? This is called the vertical line test. And again, if you remember what I said in the beginning of this section, everything that we look at will be a function. So this is just to get us really familiar with what a function is. So, you know, after this section, you won't ever see anything that's not a function. All right. All right. So basically, for a graph to be a function, and I'll say it passes the vertical line test, which means no vertical line can intersect the graph in more than one point. It only takes one instance. So for this one, there's a vertical line. It intersects the graph in more than one point. So vertical graph intersects the graph in more than one point. Not a function. Okay. All right, how about the one on part B? I mean, you could draw as many vertical lines as you wanted to. I don't know if it'll let me. I mean, well, it's not very vertical looking. Whee! Okay, never mind. I'm trying to be fancy and it's not working. So there's one vertical line. I'm just drawing a bunch of vertical lines. Oh, that one wasn't very good. Can you find any vertical line that would ever intersect that graph in more than one point? I hope not. So no vertical line intersects the graph in more than one point. So it is a function. All right. So, oh gosh, took me a little while to go through. Let me see what else I've got in here. All right, it's okay. I kind of got bogged down there in the beginning, but that's okay. We still have 10 minutes. So if if and when you need to leave, just go ahead. I'm going to just keep talking so I can finish this section. And then, like I said, I'll have this put up for you somewhere. I still got to find that out. I'm thinking I'm going to put it on YouTube, but I got to make sure that's okay. All right. Okay, function notation looks like this. Not sure what I just did there. Okay. Function notation. Y equals f of x. That's how we symbolically write y is a function of x. All right. The rest of that, let's just forget that for right now. So here's a table. Again, this is showing the value in billions of dollars of U.S. industrial shipments for selected years from 2014 and projected to 2040 from the U.S. Department of Energy. All right, it says if S represents the value over here for year X, so again over here, year X, S is the value, is S a function of X? So it's the same rule as before. If S is a function of X, what does that mean? Then again, S will be the output and X will be the input. Do any inputs repeat?
No.
No, ma'am.
Correct. No inputs repeat. So yes, it is. And the way that we write that, S is a function of X, okay? Or we say S of X is the function. Okay, this is typically what we do. When we write S of X, that's what we mean. It's another way to write it. It's a briefer way to write it, okay? S is a function of X, or S of X, all right? Whew. Okay, find F of, all right, so S equals F of 2035. So 2035 is the X. Got to go back up to the table. What S value goes with 2035? It's pretty easy. It's right there. True?
Yes.
So we write 1056. We say F of 2035. I already forgot what number it was. 10.50. Thank you. Equals 10.56. What does that mean? You know, because that's really what math modeling is about. It's giving meaning to all these symbols and numbers. What we're saying is that in the year 2035, 10.56 something, or what, let's go back and look at it. 10.56 billions of dollars would be the value of the U.S. industrial shipments. All right, so we just need to put that somehow in English, in an English state. So I'm going to say $10.56 billion were spent on industrial shipments, something like that. Okay, something like that. All right, for part C, when S is 8.84, what does X equal? So I got to go back in the table. 8.84 is right here. The X that goes with that is 2023. What's going on? Sometimes this thing acts crazy. There it is. So, was it 2023? So I think you get the idea. What does this mean? In 2023, U.S. industrial shipments were, or actually will be, that hadn't happened yet, $8.84 billion. Okay, now this is more the kind of stuff we'll be looking at. All right. Let me see what else. I'm gonna. Oh geez. Okay. Let's bypass number 6 for right now. That's something we can live without right now, but I do want to Like I said, if you need to go ahead, and I'll put this up online for you. All right, here we have a figure that shows the number of elderly men in the workforce in millions as a function G of the year, the selected year's T. All right, so we're just saying, hey, this is a function. We're saying G of the year is a function. Okay, so G, oh, geez. G, G is a function of X, T, I'm sorry, G is a function of T, okay? T is the year, G is the number of elderly men in millions, okay? So it says find and interpret G of 2020. So that's right here. So mathematically, we would say G of 2020 equals 21. What does that mean for us? Well, it means in the year 2020, which is now, 21 million elderly men were in the workforce, or are, I don't know. Okay. All right, what is the input, T, if the output is 19.6 million men? So here's 19.6. For my graph, 19.6 corresponds with 2030. So we would say G of 2030 equals 19.6. So the input that we're talking about is 2030. All right. Okay, what can be said about the number of elderly men in the workforce during 2020 to 2040? Right here, this little, change to red. This little piece of the graph, what can you say about that, just generally speaking? Maybe that it's decreasing. That's all I'm looking for there. Decreasing. Okay. What is the maximum number of elderly men? So looking for the highest point on the graph, it's up here. So way back in 1950, there were a lot of, what does elderly men mean? I don't know, I've forgotten. It's defined somehow. I think they made us change that in the new edition of the book from the word elderly, but I don't remember what we used. Gosh, so the highest point up there is at 45.8. Therefore, the answer would be 45.8 million. All right. And then to finish up the section, this is where we now define the word modeling. It's pretty straightforward, but this is where we take real world information and put it into mathematical form, typically a function. And so all of these examples, like the one, this graph that we just looked like, there is a function, a type of function that would model that data pretty well. And as we move through the course, that's what we'll be talking about. What kind of function would best model that set of data? So when we take a set of data, find a function that fits it well. That's called modeling. Aligning inputs, I'm gonna hang on to that also for a minute, probably till the next example. What's this? Okay. Okay. Here's one more example, which gives the number of alcoholic drinks and resulting blood alcohol percent for a 90-pound woman. Gee, not many women that weigh 90 pounds, but okay. So here's a function that actually would fit that data. And we'll be talking about that a lot more soon. So if we use the function y equals 0.05x, probably should have indicated what the variables. I don't see that. So x would be the number of drinks, and y is the blood alcohol percent. So we can see in the table for number of drinks between 0 and 9, goodness. But if we use the model, so here's the model, use the model to estimate the blood alcohol level for a 90-pound woman who has consumed 1.5 drinks. We just simply need to find y. If x is 1.5, and so I put substitute 1.5 in there, and that's how much? Should be able to do that in my head. Point. My brain doesn't want to do that right now. 0.05 times 1.5 is 0.075. Put my 5 down there. Okay. Okay, and then here's a graph of the scatter plot. Why is it reasonable to use x greater than or equal to 0? X greater than or equal to 0 means x cannot be negative. Why would it make sense here that x cannot be negative? Well, we can't have a negative number of drinks. So it makes sense, to use a graph where x is greater than or equal to 0. That's all that's saying. Okay. So that's it. I went about 5 minutes over. It's not too bad. Any questions? Like I said, this will be up for you pretty soon, pretty quickly. I'll convert this to a PDF document and put that up on D2L right away. And then I'll let you know about the recording. Sound good? Yes?
Thank you. Thank you.
Okay, how'd that go? Who was it, Brandon?
We gonna work with it. We gonna work with it.
Okay. All right. Sounds good. Well, I'm looking at y'all right now. Can you see me? I just see my aquarium. So I don't know. It doesn't like me right now. Okay, guys. Well, I'm gonna end the meeting, and unless anyone has a question, I'm still waiting. Anyone? Okay. Well, don't forget your assignments, and just let me know if you have any questions, and I'll see you next week, if not sooner. All right. Have a good one. All right. Bye. Oh, it doesn't show my calendar.